Hey AP Stats folks, we're going to finish up our unit. So in the first two sections we talked about sampling and surveys, and then we talked about experiments. In this final section we're going to be talking about using our studies wisely. So we're going to look at some concepts such as sampling variability, statistical significance. We're going to talk about simulations, which is something we'll also see in a future unit on probability. Also identifying when is it appropriate to make inferences about populations versus cause and effect. And then we're going to touch a little bit on ethics when it comes to doing studies. That one's not going to be an AP topic, but it's still very important to discuss. So let's dive right in. Researchers who conduct statistical studies often want to draw conclusions, right? We say this is making inferences that go beyond the data they produce, right? And everyone's, if you're a company, whether it's advertising or pharmaceuticals or whatever, you want to be able to do a study and then be like, look, this applies to you. So when members of a sample are selected at random from a population, you can use the sample results to make inferences about the population from which the sample came from. Okay, so anytime we're doing a simple random sample, a stratified random sample, any of those random sample methods, we can generalize the results to make inferences about the population. Now, just realize that there is going to be some sampling variability. Sampling variability refers to the fact that different random samples of the same size from the same population produce different estimates, right? This is just any given fact. Think about our classroom, for example, right? However many students we have in our class. If I were to take a sample of size 3 and average those 3 people's heights together, and then take a different sample of size 3 and average their heights together, a different sample of size 3 and average their heights together, none of those averages are going to be the same, right? It's going to be different. This is just the idea of sampling variability. It's not that you did anything wrong. It's not that you didn't do a good sample. It's just that there's going to be variability when you have different random samples. Even when making an inference from the random sample, it would be surprising if your estimate from the sample was exactly equal to the truth about the population. That's just it. It's an estimate. We're estimating something that's true about the population. We're not getting the exact value. If we were going to get the exact value, we wouldn't do a sample. We would do a census and actually get the whole population. So it shouldn't be surprising that's a little bit different. Now, if you want to have smaller sampling variability, you can change your variability by changing your sample size. So larger random samples tend to produce estimates that are closer to the true population value than smaller random samples. So in other words, estimates from larger samples are more precise. So you pick more things in your sample size. So when I was doing the example of height for you guys, instead of picking sample sizes of 3, what if I pick sample sizes of 4 or 5? Now I know we have a really small finite population for our class, but this applies to larger ones as well. You can see here, this data came from reaching into a jar, right, and seeing what percent of the beads that I pulled out were red. And you can see when I picked, sizes of 20, meaning I picked out 20 beads, the percents that were red, versus when I picked samples of size 100. It's still about the same center, right? It's still centering around the same place, but you can see how the spread is much less. The variability is much smaller because I took a larger sample size. It doesn't matter how many samples you take, but the size of the sample. That's what matters. So we use N here to signify the sample size. Let's look at an example. How much do NFL players weigh on average? So, talking about weight. In a random sample of 50 NFL players, the average weight is 244.4 pounds. So do you think that 244.4 pounds is the true average weight of all NFL players? And then which would be more likely to give an estimate close to the true one? A random sample of 50 players or a random sample of 100? So to answer that first question, do I think that the average weight is actually 244.4? No. Why? Because different samples of size 50 would produce different average weights. So it would be very surprising if this estimate is equal to the true average weight of all NFL players, right? This is that idea of sampling variability. You did fine, you took a nice random sample, but we're not guaranteed to get the exact value for everyone in the NFL. So which one is going to be more likely? Well, that's going to be a random sample of 100 players, because estimates tend to be closer to the truth when the sample size is larger. So kind of get this idea in your head of sampling variability is always going to happen, but you can have smaller sampling variability when you take bigger sample sizes. So that's some inference for sampling. What about when we do an experiment? Well-designed experiments, key there, well-designed, can allow for inferences about cause and effect. So many times back in Unit 3, I tried to trip you guys up when I would give you a scatter plot that had a strong correlation. I'd be like, hey, does this thing cause this thing? Is this explanatory responsible for the response? And so often students would fall into the trap of saying, yes, it has a strong correlation, right? R is close to 1. There's a strong positive linear relationship. Just because there's a relationship does not mean cause and effect, unless it came from an experiment. In an experiment, there are two ways to explain why the average response for one group is different than the average response for another. Option 1, the treatment does not have a different effect for the groups, and the difference in the response happened because of chance variation in the random assignment. Right? This can happen. Sometimes it really didn't cause it, but some chance variation meant, oh, there is a difference. The other option is that the treatment actually causes a difference in the average responses of the groups. When that happens, we say the results are statistically significant. So when the observed results of a study are too unusual to be explained by chance alone, we say the results are statistically significant, right? This is something you would see like in research papers, like, you know, the studies were found, like, it was statistically significant at whatever level. That means that the results weren't just because of random variation or chance variation, right, in the random assignment. It was actually caused by the treatment. Let's go through an example for this inference. Anybody ever watched the TV show Mythbusters? This was one of my favorites back in the early 2000s. So the Mythbusters team conducted an experiment involving 50 subjects. Each subject was placed in a booth for an extended period of time and monitored by a hidden camera. 34 subjects were given a yawn seed by one of the experimenters. So what that means is the experimenter yawned in the subjects present before leaving the room. And the remaining 16 subjects were given no, like, yawn seed. And so we want to know what happened in the experiment. The table shows it here. So you can see whether or not the subject yawned compared to whether or not they were given the yawn seed. So the way you would read this, of the 34 people who were given the yawn seed, 10 of them yawned and 24 of them different. Of the ones that didn't receive the yawn seed, of those 16, 4 of them did yawn and 12 of them did not. So let's answer some questions about this. Let's calculate the difference, yawn seed versus no yawn seed, in the proportion of subjects who yawned in the two groups. So you can see that there were 10 out of my 34 that yawned, who were given the seed, versus 4 out of 16 who yawned who were not given the yawn seed. So if you convert those fractions into decimals, the difference in those proportion is 0.04. Okay, so pretty small. So instead of doing another experiment, we did a simulation. Right? A simulation is using what you are assuming about your value to see, like, well, would this really happen if I did many, many more, many more, like, iterations of this experiment. So we did a total of 100 trials of the simulation were performed to see what differences in proportions would occur due only to chance variation. Okay, so this is an experiment, it's just by chance alone. Assuming that the yawn seed doesn't affect whether the subject yawns. So meaning, would you just happen to have 14 people that yawned and 36 that didn't, if they were randomly assigned to groups of 34 and 16? Here is my simulation of differences. Okay, so you can see some negative, some positive, right? In the previous example, we had 0.04, so that's going to be close to here, close to 0. All right, let's do some reading. So there are 5 dots at 0.23. So 1, 2, 3, 4, 5. What do these dots mean in context? Well, in the context of the problem, when we assumed that yawning is not contagious, meaning it can happen by random chance alone, there were 5 simulated random assignments where the difference in the proportion of people who yawned was 0.23. So that's how you would interpret that dot plot, those dots on that location. Now, use the results of the simulation to determine if the difference in proportions from part A is statistically significant. Explain your reasoning. So 0.04 is about here, right? There's a lot that are in that area. Because a difference of 0.04 or greater, right? I don't want to look just there, but I want to look at this or more, occurred 56 out of 100 times. How do I know that? I could count up all of these dots, and it would be 56. That's a lot of times, right? It wasn't unusual. That means the difference is not statistically significant. So it's quite plausible to get a difference this big simply due to chance variation in the random assignment. Now, if I had done this and it only happened like, I don't know, less than 5% of the time, then I would say, yeah, that's statistically significant. We usually use 5% as our kind of cutoff for whether it's statistically significant or not. So if you're looking at a simulation, if there's a lot of dots in that value or in the extreme, so in this case I did more than as opposed to less than because there were fewer that were more than, but it was still a lot. Yeah, we're not going to say statistically significant. There's another great example of this in your textbook as well. So check out that example because this is probably one of the big things that people get confused on is using these dot plots and simulations to figure out whether things are statistically significant. All right, let's look at some types of inference. So you can get an inference about a population if the sample was randomly selected. And again, this can only be an inference about the population from which the sample was selected. So if you did a random sample at Eastern Mennonite School, you could then only apply your results to Eastern Mennonite School because that's the only people you got your data from. Like that was the pool from which you sampled. But if you did all high schools in Harrisonburg and Rockingham counties, then you can apply your results to all those schools in those places. But it's not every high school student ever. And again, you can infer about cause and effect if the groups were randomly assigned. So the perfect storm is if you have both random selection and random assignments. So let's look at our next example here. Many students insist that they study better when listening to music. A teacher doubts this claim and suspects that listening to music actually hurts academic performance. Here are 4 possible study designs to address this question at your school. In each case, the response variable is going to be the student's GPA at the end of the semester. Pause this video and take some time and read through all 4 of these different study designs, and we're going to figure out what does this mean as far as the inference. So literally pause this video and read through these. For the first one, what can we infer? Well, there was no random selection here, and so the results of the study can only be applied to the students that were in the study. And also, since there was no random assignment, we can't conclude anything about cause and effect. So the only thing that you can say is that AP Stat students who listen to music while studying have lower GPAs than those who do not listen to music while studying. We don't know why, and we can't say this about anyone else, any larger group. Next example. There was random selection, okay? So the results of the study can be applied to the entire population, in this case, all the students in the school. But again, there was no random assignment, so we can't conclude cause and effect. So all we can say is that students at this school who listen to music will have lower GPAs than those who do not listen to music while studying, but we don't know why that happened. All right, we can't say the music caused it. Third scenario, there was no random selection, so the results can only be applied to those AP Stat students that were in the study, but there was random assignment, so you can conclude there is a cause and effect relationship between listening to music while studying and GPA, but that's only for the students that took part in the study. And then finally, there was random selection and random assignment, so we can infer this to the whole population as well as a cause and effect relationship. Stay tuned for one more video in this section.